Alrighty, so something happened in my first recording. I apologize about that. But we were using the compound interest formula to solve this problem where it says suppose $1,000 is deposited by a 20-year-old worker, which we don't actually care about the age of the worker. We just know that it took 45 years before this worker took their money out of the account or took a look at the account to see how much was there. So if the money was compounded quarterly and annually, or what we're looking at to see the difference in the amount. So compounded annually, that means one time a year. So we're going to take our equation, principal times one plus the rate divided by how many times a year to the n times t power. So we're going to just basically input these things. $1,000 is our P. 1 plus the rate divided by 1 time, and 1 times 45. You're going to put that directly in your calculator. You don't have to do these things by hand. You're literally going to type it into your calculator. And when you type that into your calculator, you'll get your value out. But before we do that, let's just look at quarterly. So quarterly is the same information. We have $1,000 for the principal, 12% interest rate, but quarterly means it's going to be 4 times a year. And then it's going to be for 45 years. And so in this case, we're going to have $1,000 for our principal, 1 plus 0.12 divided by 4, and then 4 times 45. So you see that exponent is going to be a lot larger this time. So if this money is compounded quarterly, then you're going to end up with $204,503,036. I'm sorry, $503.36. I said that all wrong. Let me say this better. I'm sorry. You're going to end up with $204,503.36. I don't know what I said at first, but that is how you say that. And in this other case, when it's just compounded once a year, we ended up with $163,987.60. So notice that just compounding that money more times a year, that interest rate is going to be growing a lot faster, and you'll end up with a lot more money. So you just take this value and subtract the other, and you'll end up with a difference of $40,515.76, which basically says that, hey, because of the high interest rate and the long period of time, the quarterly compounding results in an increase of $40,000. So if you are working on your savings accounts right now, you want to get a high interest rate, and you also want to leave it in there for a long period of time. Okay. All right. So let's apply these concepts additionally in like one different way. So you can compound annually, quarterly, monthly, biannually. You can do it so many different ways. The more you compound it, the more interest you're going to gain. But there's something called compounded continuously, and that requires us to use the natural exponential function, and that's e. The number e is just like pi. It's an irrational number that just doesn't stop. And so this is an approximation for e. 2.718281828, and it just continues and continues. And so when we're talking about, and that's called Euler's number. This is, it says Euler, but it's really Euler. That's how you pronounce it. Um, so compounded continuously means it's compounded every second, every millisecond of the day. And so you can notice that it's probably going to be grow faster at that rate as well. So in this case, the principal of the IRA is $1,000. We're still going to operate on a 12% interest rate, but this time it's compounding continuously. So then we don't have an end, but it's still going to be for those 45 years. So we're going to use our PERT formula, which is the principal times e to the RT. So that's 1,000. And then we're going to have E, which is a value on the calculator, to the RT. And so the rate is 0.12 times the time, which is 45 years. Okay. And so what we get here for our amount of the bank, I'm sorry, after 45 years is $221,406.42. So recall that when it was compounded quarterly, we made the 204,000, what was it? $204,503.36. Well, now we have $221,406.42. So when we subtract that, we do see that this is 16,000 more than that. More than the quarterly compounding. So let's just talk about this one more time. If it was compounded just one time a year, you would only have $163,000. But then you realize, okay, the more I compound it, the more I actually get. So compounding it 4 times a year gets you $40,000 more. So you're like, hold on, that's 4 times a year. What if I do it 12? What if I do it 365, compound it every day? What if I compound it every minute, every second? Oh my God. That is how we get to compounding continuously. And remember the E, this is a button on the calculator. Okay. So yeah. Now what we'll do is we'll apply this concept in with our exponential growth factors and stuff one more time just so that we can make sure we understand it. So the number of people who are 100 years older or more, I'm sorry, old or more, are called centenarians. I can never say this word. Centenarians. That means they're 100 years old or more. This number in India is projected to increase by 4% each year after 2010 until 2100. If there were 50,000 centenarian people over 100 in India in 2010, write a function f that gives the number x after 2010. So basically, my C value is 50,000 because that's how many they started with. Okay. So now we need to find the growth rate. The growth rate, it says that they're increasing by 4%. So we have 100% plus 4. That gives us 104%, which in decimals is 1.04. So our formula is going to be 50,000 times 1.04 to the x power, where x is the number of years after 2010. So that means 2011 would be 1, 2012 would be 2. So it says project the number of people over from 100 in 2050. 2050 is 40 years after 2010. Okay. So what we're going to do here is we're going to just take our formula and we're going to substitute 40 in for x. So x is going to be 40. Because remember, it's the number of years after 2010. So that's 40 years later. F of 40 equals with 50,000 times 1.04 raised to the 40th power. And what we'll find when we substitute that in our calculator is that it's about 240,000 people. So in 2010, they had 50,000, but by 2050, they should have 240,000 people that are over 100. So this time we're going to be doing half-life. So if the quantity initially equals C, so that's our initial value still, and it has a half-life of K, then we're going to use this formula. C, the growth rate is 1/2. but it's going to be to the time divided by how much ever the half-life is. So radioactive carbon-14, which is found in all living things, has a half-life of about 5,700 years and can be used to date fossils. This is how they figure out how many years ago dinosaurs roamed the earth. So A of T, in this case, we're looking at a 24,500-year-old. That's for time. T equals 24,500-year-old fossil. Okay. And then our K is 5,700 years. Okay. And then C is the organism starts with 100% of like carbon. So our C is going to be one, like a whole. It's a whole person, a whole fossil, a whole whatever it is. So our C value is 1. Our growth rate is 1/2. And then the time is 24,500 years divided by the half-life of carbon, which is 5,700. And you'll just put this in the calculator and you'll find that A of 24,500 is actually equal to approximately, rather, 0.05. That's a percentage. So 5% of carbon 14 remains after 24,500 years. So like let's say an organism dies 24,500 years later, about 5% of their carbon-14 is still there. That is the end of 5.3. I hope this helped.